Hi, I'm Beth Faber of the Hydrologic Engineering Center, and this is the third video of lecture 3.6. This is prospect course number 209, risk-based analysis using the FDA software. And lecture 3.6 is on uncertainty in exceedance probability functions or frequency curves. This third video is on the hydrologic modeling approach for estimating flow frequency curves. I have a lot less experience in hydrologic modeling, so I'll have a bit less to say about the basics of this approach. But hydrologic modeling is rainfall runoff modeling. So we're using a modeling tool to transform rainfall into stream flow, right? So it needs to capture precipitation, infiltration, runoff, channel routing, and other aspects of the process, maybe snowmelt. One modeling tool that you can use is the Hydrologic Modeling System, or HMS. This is a tool that must be properly calibrated to be useful. In this approach to building a flow frequency curve, we're going to simulate a range of frequency-based precipitation events to compute a flow frequency curve. There's various different types of uncertainty in the modeling approach. Okay, the very first is the boundary condition uncertainty. The boundary conditions are the precipitation data and other atmospheric variables. So the primary input is going to be based on precipitation frequency analysis and a precipitation that has a specified exceedance probability. So precipitation frequency analysis is similar to the flow frequency analysis that we've been looking at. But while flow frequency analysis and a flow frequency curve is very dependent on the watershed, in precipitation frequency analysis, we expect a lot less difference from location to location. So we can have a few gauges that are far enough apart to provide independent observations, but that we might assume the observations are estimates from the same probability distribution of precipitation. So we can pool those observations together in an approach called regionalization. Regionalization is also called trading space for time, because we're taking data from different gauges that are different in space and pooling those observations to approximate having more time. So we can consider regionalization by thinking back to workshop 2.3 at the beginning, when each of you was rolling a 6-sided die 12 times to estimate the probability of rolling a 4. So if we were doing this class in HEC's classroom together, you'd have all been rolling an identical 6-sided die. With an identical 6-sided die, we would have assumed that the probability distribution you were each trying to estimate was the same. So we could have pooled the 12 rolls each from 45 students to have 540 rolls, right? So a sample of size 540 would have provided a much better estimate of the probability of rolling a 4 for those identical dice. So that would be a form of regionalization, okay? So precipitation frequency analysis, having the ability to use regionalization, provides the equivalent of a lot more data, right? So this is a precipitation frequency curve. These analyses, these regional analyses, are generally done by NOAA as opposed to being done for each individual study. This is a frequency curve from NOAA Atlas 14. And as you can see, it uses a different horizontal axis than we were showing for flow. But notice that the average occurrence interval or return period is going out to 1,000. The ability to pool data and thus having the equivalent of a lot more time, the curves can be approximated with more confidence further out, right? So the equivalent record length of a precipitation frequency curve is going to be quite a bit higher than the equivalent record length of a flow frequency curve, right? So our first input might have less uncertainty for this method, but then we have to bring in all the other uncertainties that are involved with the hydrologic modeling. Right, so we have uncertainty in the initial conditions, the soil moisture, the channel base flow, the other inputs that we have to define at the start of the simulation. So we have model uncertainty, which is selecting the correct representation for each of the hydrologic processes we need to model. And then we have parameter uncertainty. So each of those process representations is defined by parameters that need to be estimated. Right, so all of these uncertainties contribute to the uncertainty in the estimated flow frequency curve. This is the frequency curve I mentioned for the boundary condition uncertainty. Right? So here are some parameters from the green and amp infiltration method, being shown here as probability distributions to capture the knowledge uncertainty in those parameter values. Right? Model uncertainty. Here's a depiction of the calibration process and how even with the best calibration we can attempt, we're going to have some difference in the modeled flow versus the observed flows. So when do we use the modeling approach? Modeling approach is necessary when either flow observations are not available or when flow observations might be available at one site, but we need flow frequency curves throughout the watershed. Right? The assumptions are that the hydrologic model can adequately represent the physical processes that transform rainfall into runoff. Also, that the relationship between precipitation probability and flow probability is known. Using a model like HMS can let us address watershed properties that change over time. They can let us analyze future conditions in the watershed. Of course, that requires an estimation of what those future conditions will be. So developing the model, we're going to delineate subbasins, reaches, and junctions. And we have to make sure that we have junctions at every location where either a flow frequency curve is needed or where flow observations are available. The initial parameter estimates for model components will be estimated from terrain data, soil property maps, land use maps, and other sources. And several historical events should be used to calibrate the model if at all possible. So for developing the frequency curves, there's two approaches that we're going to discuss. The first is when we have a frequency curve within the watershed, because we have at least one gauge site within the watershed, but we want to expand that to have frequency curves at other sites. And then there's the situation where we don't have gauge data at all. So this slide first discusses a situation where we do have a gauge site within the watershed, and we want to develop frequency curves for several other sites as well. So the first step is generating a flow frequency curve at the gauge site using the observation approach that we discussed in the last lecture. Then we develop frequency-based precipitation for each exceedance probability X. So this is based on our precipitation frequency estimates that are perhaps from NOAA Atlas 14. Next, we're going to essentially calibrate the model to that flow frequency curve at the one site. Right? So we're going to calibrate the infiltration components so that the X% exceedance precipitation produces the X% exceedance flow. In some cases, it won't be possible to find infiltration components that make sense, that can line up the X% precipitation to the X% flow. And in that case, we just have to keep track, right, of what exceedance probability of precipitation is going to line up with what exceedance probability of flow. So finally, we're going to apply the full range of frequency-based precipitation events across the watershed. So having calibrated those precip events to the site in which we do know flow frequency for each of the different flows, we'll now be able to use the flow at all the other sites with each exceedance probability to produce a flow frequency curve for each of the other sites. Now that's how it works when we do have one gauge site within the watershed and we're able to develop that one flow frequency curve. If there aren't any gauge sites within the watershed, we are skipping the first and the third step. We start by developing the frequency-based precipitation events for each of the different exceedance probabilities that we need. And then for our watershed that's at least maybe been calibrated for some local events, we're going to apply that precipitation to the watershed and compute flow at all the points that we need, and have computed then a flow that's going to go with each of those exceedance probabilities. So in that case, we're assuming that an X% exceedance flow is produced by the X% exceedance precipitation, right? So the 1% precip gives the 1% flow. Now we need to consider the uncertainty that we have in the resulting flow frequency curve. We're going to parameterize uncertainty based on equivalent years of record, right? So in the same way that we described it when we actually have a frequency analysis, we're going to describe the uncertainty in the same way, but with an effort to state the value of the curve or the uncertainty in the curve based on an equivalent years of record. So this is a table from EM 1619. It describes some assumptions for equivalent record length. The first is if we've done a frequency analysis with a gauge available at our site of interest, and it says the equivalent record length is just equal to the systematic record length. The systematic record length is the gauge record. Okay? Next, we have situations when we have a gauge that's nearby. First, a gauge on the same stream with drainage area within 20%. They're saying 90 to 100% of the record length can be used for the equivalent record length. Then we've got a gauge within the same watershed. And then we have somewhere between 50 to 90% of the record length being appropriate as the equivalent record length. Next, we move on to rainfall runoff modeling. The first is a rainfall runoff model calibrated to several events within the watershed, and they say that was equal to about 20 or 30 years. Then we have a rainfall runoff model that was not calibrated and instead is using regional parameters. Okay, that's called equivalent to 10 to 30 years. That might even be a typo and should be 10 to 20. Then finally, a rainfall runoff model that doesn't even have regional parameters and is just using handbook parameters, right? And that's 10 to 15 years. So as you can see, the assumed record length is quite a bit less for the rainfall runoff modeling approach. So let's move on to how we bring this estimated frequency curve into FDA. So if the estimated frequency curve is relatively smooth and looks like it can fit a log Pearson type 3 distribution or be represented by a log Pearson type 3 distribution, we have the option of approximating the log Pearson type 3 statistics with a method called synthetic statistics that was described in Bulletin 17B. Right, so in the FDA analytical frequency curve window, instead of entering log Pearson type 3 statistics, as we did from the flow frequency analysis based on gauge data, we're choosing compute synthetic statistics, and we enter a median, a 10%, and a 1% event, or a 2-year, 10-year, 100-year flow. We enter those 3 flow values, and FDA will use the synthetic statistics method to calculate an equivalent mean, standard deviation, and skew that matches the upper half of that curve. We're also entering the equivalent record length to describe the uncertainty. If we don't feel that a log Pearson type 3 distribution will fit appropriately, then we enter the information as a graphical frequency curve. So back at the hide-eng menu, we choose exceedance probability functions with uncertainty, but when given the choice between analytical and graphical, we now hit the graphical button. Right? We choose discharge probability, and then we can enter the graphical curve as exceedance probability versus discharge. We type in this table, and then again we enter the equivalent record length to describe our uncertainty. When entering this table, it's important to remember that we have to describe the entire range of probability. Right? FDA will not extrapolate below the lowest or most frequent event, but it will extrapolate above the highest or least frequent event. But the range of values that we describe can affect the computed uncertainty. So after entering the table, we come back to this screen. FDA has used an uncertainty approach called order statistics to compute the standard deviation of uncertainty at each of these flow quantiles. It pairs that with a normal distribution. So it offers to you the curve plus and minus 2 standard deviations and plus and minus 1 standard deviation. When you hit plot, it plots the entered curve in red and then the plus 2 standard deviations and minus 2 standard deviations curve. Now keep in mind that since it paired with a normal distribution, plus and minus 2 standard deviations produces a 95% confidence interval. Now, in the same way we looked at how the LP3 distribution would be randomly sampled with an FDA, we also have to revisit how a graphical frequency curve would be randomly sampled with an FDA. In this case, we choose a random curve based on only one random number, uniformly distributed between 0 and 1. So using that order statistics method to describe the standard deviation and paired with a normal distribution, we have an uncertainty PDF, again, imagined as coming out of the screen. We have these PDFs along the range of probability, and we can consider the percentiles of all of those PDFs. So what we're seeing here is an array of percentile curves that are also called parallel curves. Right? They're not actually parallel, but they all represent the same percentile of the uncertainty. And each of them is spanning some percentage of the uncertainty reflected by the area under these PDFs. So we have maybe 10% of the area spanned at this point, then 20, then 30%. When we choose a random number between 0 and 1, let's say we choose 0.23, we come up to 23% in these parallel curves, and that produces the flow frequency curve that FDA will use for that realization. So here are some situations in which developing the curves is not quite as straightforward. So regulated flow frequency curves. Reservoir regulation changes the natural flow frequency curve, and the log Pearson type 3 distribution might not be appropriate. Right? So in this case, we're going to pair our hydrologic model with a reservoir model, right, to compute channel flow that incorporates regulations such as reservoir operation or maybe diversions. Right? That'll let us determine the regulated flow for a range of probabilities. That creates a regulated flow frequency curve, which we can bring into FDA as a graphical curve. Right? And that's considering the hydrologic modeling method. To consider the observation approach or gauged frequency flow approach, we might have observations of the regulated flows. And if they represent a consistent regulation across time, we can take our regulated flow record and its annual maximum flows and sort and plot those values against plotting positions and do a graphical fit or an empirical fit of the frequency curve. Right? If our record does not have a consistent regulation across time, we can maybe back out unregulated flows above the regulation and then route that unregulated record through the same reservoir model to get a record of regulated flows. And again, estimate an empirical frequency curve by ranking and plotting versus plotting positions and drawing a graphical curve. Right? So that would also then be entered into FDA as a graphical curve. Right? Another situation is with stage. Very flat channels or with tidal influence or backwater make it very difficult to estimate a one-to-one relationship between flow and stage, which FDA needs as its second summary relationship. With backwater, if there's not a one-to-one relationship between flow and stage, and we can't expect to be able to put in a flow stage relationship within FDA, then we need to start the process with a stage frequency curve instead. So we've replaced our first two summary relationships, flow frequency and flow stage, with a stage frequency curve as the first step. So in this case, we're going to pair our hydrologic model with a hydraulic model to go directly to computing channel stage. And that's going to give us a stage for each of our exceedance probabilities, generating a stage frequency curve, which would be entered into FDA as a graphical curve. Again, thinking back to the observation approach, if we have observations of stage, then we can again rank them, plot them versus plotting positions, and estimate an empirical distribution or graphical distribution by the observations. That would again be brought into FDA as a graphical curve. So if you have questions about the hydrologic modeling approach, please go to the discourse site and enter those questions, and I'll try to be watching real time and be able to provide some answers. So a quick summary of this lecture. We just described two different methods for estimating flow frequency curves. There was frequency analysis of observations and fitting a log Pearson type 3 distribution to unregulated flows. And then there was rainfall runoff modeling of frequency-based precipitation. Right? We talked about the sources of uncertainty in each of the methods. We characterized the uncertainty by an equivalent record length in both cases. And then we entered the analytical distribution or graphical distribution into FDA, including the equivalent record length to describe the uncertainty. Right, so that's the end of the third video of lecture 3.6. Thank you for joining me.